At the very heart of robotics, there's this really fundamental question we have to answer. How do we even talk to a machine about movement? How do we give it a precise command for where it should be and exactly how it should get there? It's all about creating a language of motion. So let's just jump right in with a question. You look at a robot arm like this one, just how many different, independent ways can it actually move? It seems like a simple question, but the answer is surprisingly deep. Yeah, because for a beast of a machine like this industrial manipulator, it's not just one simple number. Every single joint, every link, it all plays a part in where that arm ends up. To make sense of it all, we need a system. And the system we're going to explore today, it's actually incredibly powerful and, dare I say, pretty elegant. And to answer that big question, we have to start with the most basic building block in pretty much all of robotics. It's a concept called degrees of freedom. Okay, so the textbook definition goes something like this. The degrees of freedom, or DOF for short, is the minimum number of coordinates you need to completely describe the position of every single part of the robot. You can think of it like the robot's unique fingerprint of movement. But, that's a bit dry. Here's a much better way to think about it. Just imagine you have a control panel for the robot with a bunch of knobs on it. The number of degrees of freedom is simply how many of those knobs you have to turn to put that robot into any possible position it can reach. It's the number of independent controls. All right, let's start as simple as we can. 1 degree of freedom. Think about a simple door, right? It's a rigid object, but it can't just float around. It can't go up, down, or side to side. It can only do one thing, swing on its hinge. That means it has exactly one control knob, its angle, and that's it. 1 degree of freedom. Okay, pretty simple. So let's level up. What would a system with 3 degrees of freedom look like? A coin on a table is just a perfect example of this. So we need 2 knobs to tell us its position, right? One for sliding it left and right, that's our X, and another for sliding it up and down, that's our Y. But wait, that's not quite enough, is it? We also need a 3rd knob to describe which way it's facing, its rotation. So that gives us 3 independent control knobs, 3 degrees of freedom. All right, now that we've got the basic idea down, we can scale this whole thing up. We can go from simple objects like doors and coins to any solid object, like a single part of a robot just floating around in 3D space. And it turns out, in our 3-dimensional world, there's kind of this magic number. For any object that isn't bolted down to something else, that number is 6. And this is a really crucial point. An airplane, a satellite, even just one of those metal links from the robot arm we saw earlier. If it's floating freely, it has exactly 6 degrees of freedom. 3 of those control knobs tell you where it is in space, your classic X, Y, and Z coordinates. And the other 3 tell you its orientation. You can think of that as its pitch, roll, and yaw. 6 numbers, that's all it takes. Okay, so this leads to a really, really good question. If a single link has 6 degrees of freedom, and our robot arm has, say, 6 links, then why doesn't it have 6 times 6, or 36 degrees of freedom? I mean, the math seems to add up, but it's totally wrong. And the reason why it's wrong is the key to understanding how all robot mechanisms actually work. The answer, it turns out, lies in the joints. The joints are the rules of the game. They dictate how the links are allowed to move in relation to each other. You see, a lot of people think joints add freedom, but it's really the opposite. They primarily take it away. They act as constraints. Once a link is connected by a joint, it's not free anymore. The joint forces it to follow a very specific path, and in doing so, it removes most of those 6 potential freedoms we just talked about. And what's so cool about this slide is how it spells it all out. Take a look at a revolute joint, which is really just a fancy word for an elbow or a hinge. It allows 1 degree of freedom, rotation. That means it's imposing 5 constraints. It's forbidding the link from moving in all those other 5 ways. And it's the exact same story for a prismatic joint, the kind that slides. 1 freedom to move, 5 constraints. And that is why our 6-link arm doesn't have 36 degrees of freedom. So now we have all the pieces, right? We have degrees of freedom and we have joints acting as constraints. With these building blocks, we can finally draw a complete map of every single possible pose a robot can get into. And this map has a very cool name, configuration space. A robot's configuration space, or C-space for short, is this abstract space where every single point on it corresponds to one unique configuration of the robot. So if your robot has, say, n degrees of freedom, its C-space is an n-dimensional map. And when you move the robot, you're basically just tracing a path on this map. And the shape of this map isn't just random. It's a fundamental property that comes directly from the robot's physical design, its specific combination of links and joints. A different robot will always have a different map, a differently shaped C-space. And this slide just brilliantly shows how weird and wonderful these maps can be. On the left, you have a simple arm with 2 rotating joints. Okay, pretty standard. But the C-space for this arm is the surface of a donut, a torus. Now, why on earth is it a donut? Well, think about it. The position of the first joint can be plotted anywhere on a circle, right? 360 degrees. And for each of those points, the second joint can also be plotted on its own circle. And when you combine those 2 circles, you get the shape of a donut. Every single point on the surface of that donut is one unique pose for that arm. How cool is that? Now, that abstract donut shape might seem a little out there, but it's directly tied to the robot's physical structure. In fact, we use that structure to classify the 2 main families of robots, open chain and closed chain. So on one side, you've got open chain robots, just like the arm we've been looking at. It's basically a simple series of links, one after the other. Calculating its degrees of freedom is super easy. You just add up the freedoms from each joint. But on the other side, you have closed chain robots. See how the links form these closed loops? A flight simulator platform is a classic example. These loops add a whole bunch of extra constraints, which makes figuring out the total degrees of freedom way more complex. But it's also what gives these robots their incredible strength and rigidity. So let's just take a step back. We've built this incredibly powerful framework. We can precisely define a robot's freedom of movement, and we can even create a complete map, its C-space, of every single place it could possibly go. Which leads to one final really big question. If we have the perfect map, what's stopping us from planning the perfect path for the robot to get anywhere? Well, the answer, of course, is things like obstacles, physical limits, the sheer dynamics of motion itself, but that is a story for our next explainer.